Dear students, in the last session we have seen P series. Today we shall see Cauchy's root test. Let us see the theorem. If sigma an is a positive term series such that limit n tends to infinity an all to the power 1 by n is equal to L, then the series converges if L less than 1, diverges if L greater than 1, and the test fails to give any information if L is equal to 1. Let us see the proof. It is given that limit n tends to infinity an all to the power 1 by n is equal to L. Now, by the definition of limit, for given epsilon greater than 0, there exists a positive integer m such that modulus of an all to the power 1 by n minus L is less than epsilon for all n greater than or equal to m. Now, by using property on modulus, this inequality can be written as an all to the power 1 by n is greater than L minus epsilon and is less than L plus epsilon for all n greater than or equal to m. Now, removing the first m terms of sigma an, we have an all to the power 1 by n is greater than L minus epsilon and is less than L plus epsilon for all n. I have written here for all n. This is because we have removed first m terms of the series. So, now this inequality holds true for all the values of n. Take this as 1. Number this as 1. Now we shall see the three different cases. Case 1. When L less than 1. Choose epsilon such that L plus epsilon is still less than 1. We have L less than 1. Now choose epsilon such that L plus epsilon is still less than 1. Now put L plus epsilon is equal to R. Then R is less than 1. Now considering right side portion of the inequality, in 1 we have an all to the power 1 by n less than R less than 1. This inequality implies an is less than R power n for all the values of n. Now, see the series in the RHS, that is sigma R power n, is a geometric series with a common ratio R less than 1, and so it is convergent. Now, by first comparison test, sigma an is also convergent. Hence, sigma an is convergent if L less than 1. Let us move on to case 2. When L greater than 1. Choose epsilon such that L minus epsilon is still greater than 1. We have L greater than 1. Now choose epsilon in such a way that L minus epsilon is also greater than 1. Now put L minus epsilon is equal to R. Then R is greater than 1. Now by inequality 1, an all to the power 1 by n is greater than L minus epsilon. And L minus epsilon is equal to R and R is greater than 1. This implies an all to the power 1 by n is greater than R, which implies an is greater than R to the power n. Now see the series in the RHS, that is sigma R power n, being a geometric series with the common ratio R which is greater than 1 is divergent. RHS series is now a geometric series and is divergent. So by second comparison test, sigma an is also divergent. This is when L greater than 1. So this completes case 2. Let us see case 3, that is when L is equal to 1. This we shall see by considering example. For this I am taking two series, sigma 1 by n and sigma 1 by n square. Both are P series. You have already came across P series, how it behaves. See, this is a P series, that is sigma 1 by n is a P series with P is equal to 1, and so it is divergent. And sigma 1 by n square is a P series with P is equal to 2, which is greater than 1, and so it is convergent. One series, that is sigma 1 by n, is divergent and this series is convergent. But for both the cases, limit an all to the power 1 by n as n goes to infinity is 1. So Cauchy's root test fails to give any information when L is equal to 1. This is the proof of the theorem. So what Cauchy's root test says? If sigma n is a positive term series such that limit of an all to the power 1 by n is equal to L, then the series converges if L less than 1, diverges if L greater than 1, and it fails when L is equal to 1. Okay, dear students, let us see in the next session.